The simplest possible bond that one could imagine is a bond that only has two parameters. It has a tensile strength and it has a shear strength. And it's going to allow this, so therefore it can break in tension, it can break in shear, and it acts over a vanishingly small area. So just think, it's just like, think of two metal marbles, and when they're touching, there's like a little tiny bit of glue that joins them. Okay, because it's a super tiny amount of glue, if I try to rotate these relative to each other, think about it. If I rotate two surfaces relative to each other, there has to be a finite width surface so that I can make compression on one side to balance with tension on the other. This guy doesn't have that. It has a normal strength and a shear strength. So this is the next level of contact model that's available. This is called a contact bond model. Okay. Um, The idea is when it's bonded, notice that's a fuse that can break. Notice also I can pull it up and down. It can start to take tension, but eventually this will break in tension. Notice in the shear direction, there's a fuse. It's bonded. Notice there's no frictional interaction between the surfaces because there's glue there instead, right? If it breaks, if either of these break, boom, it turns into an unbonded system. It behaves like this, okay? So that model has the linear model parameters, but it also has two additional parameters, which are tensile strength and shear strength. And that's why we call this the linear contact bond model, because when the bond breaks, it's the same exactly as the linear model. Okay. Um, Again, looking at this, notice normal force, normal displacement. And now when a gap opens up, I start up getting tensile force, and then it breaks. And when the shear behavior, it loads up at KS and it reaches a point, boom, and it breaks. And when it breaks, it reverts to the uh, linear behavior with the friction coefficient. When it breaks, turns to a linear model. Okay. Now let's look at that. I'll dem 2. So if we run that, call dem 2. Now, same thing. So it's like if I went to a pool hall and did this with somebody, but this time I glued these things together and the guy doesn't know they're glued together. Okay, now I'm going to shoot this. Now notice we're going to look at the force chains. And this time we're going to also see tension developing. And so the tension is going to be red lines and the compression is going to be black lines. Okay. And this is infinitely strong glue. And remember, again, there's no damping and there's no friction. So now if I run this thing, watch. What am I seeing? It's a whole bunch of masses and springs, and those springs are going tension, compression, tension, compression. Think of this as a wave too. I hit it. A compressive wave went through the system, which started then bounced back as tension and then compression. And so this is you could think of this thing. You could think of this thing. Let's run it from scratch again. This is a bonded particle representation of an elastic body, and it's not breaking. It's an elastic body. This is what would happen if I had a hunk of guys glued together, right? I hit it, and now they start bouncing around, and the wave can't get out of it. So it's going tension, compression, and it's all hanging together. Okay. I love this picture. This illustrates so much. So in terms of what the key element here is, one thing to take away is that now you can have tension in the system if you have some type of bonding. Okay. Now, just for fun, we're going to we're going to do the same thing, but this is going to be PFC 3D model, and it's actually the modern PFC 3D. Now things get, wait, one other thing. This system in PFC 2D, okay, You can think of this as, okay, check this out. Someone came up with this idea. This is when you go to a bar, you can play billiards, but you can also play air hockey. So it's a big table. It's about as big as a billiard table. It's long and narrow. There's a little slot on one side where you need to defend. You don't want this thing to go in. What do you have? You have a table with a very large number of little holes. And what happens is a blower turns on and there's air blown out of all those holes. And so then you have a disc that's supposed to be like a fake hockey puck. It's black disc, and that disc floats on the cushion of air. And so you hit it, you hit it with your hand, and it just bounces all over the place, and it's almost frictionless. That's what this is behaving like when there's no friction, right? It's just an air hockey table, and it's blowing itself, moving around. Now in 3D, it's a more complicated system, right? Now we have these spheres. Now we have to have gravity on, and now we have to have a wall, which is a surface. I made it green because billiard tables often have green felt. And so gravity first has to get turned on, and they have to come to equilibrium. So you're going to notice that when we look at this, there's going to be a compression force at the bottom of each one that keeps it from going through the table. And the same thing here. And then we're going to give this guy an initial velocity, and the same thing is going to happen. It's going to hit this, blow them away. So let's see what happens here. This is in tutorials, my pool table. So I'm going to fire up PFC 3D. It takes a few seconds. Don't worry about the details. We're just going to run this thing and look at it. So here we go. There's my system ready to rock. See that? It's a 3D system, right? So now I'm going to cycle it. Boom. And they go away. And since gravity's on, actually, if we keep looking at this, see these guys, they're going to start going down. See how that guy's going down as we continue. Okay. Shift escape. There they are. Okay. Now, we can also play the game of putting bonds on between them all, just like the other case. And now, wait, before we get to that, let's zoom in here. Let's turn off the balls. Those are the contact forces. They're all compressive underneath each one. Now, to make even it more exciting, we're going to make the balls transparent. Oh, no, we're not going to make them transparent. You can't really see what's going on. Let's look at it from this perspective. Now, boom, hit it. There, it's vibrating around. Let's continue. Million cycles. Oh, let's turn off the balls. There we are. Contact forces, black and red, black and red. Just because we can, this contact model cannot resist graphics. Shift escape. What do I got to do? Shift escape. Oh, there we go. Oh, it is refreshing. Look. These contacts cannot resist local micro moment, which means they can't hold their shape. So this guy's going to just work his way like a big worm. Going to go off the edge. Remember, gravity's on. And now he's flying in space. He's still vibrating all over the place, and he's falling. Run it again. Just to show that, right? Hit that thing. Continue, boom. And there she goes, vibrating back and forth. Okay. Discard that, go back to this. All right, let's introduce the next type of bonding. Let's shut this off. Now we go. The next level of bonding is going to be a bond that can also resist moment. Okay. This is what we're going to call a parallel bond. And I'll tell you why it's called parallel in a moment. We call it a parallel bond. And what it does is it's as though we put cement here. Think of having two balls and now smearing cement in that region there between them. So here's my cement. I made it red. So what does this have? This has two surfaces pushing against each other, just like the linear model, but it also has additional springs representing the cement. And these springs are acting in parallel. There's a spring here, and there's these springs on the sides. So they're acting in parallel. We call it a parallel bond. This thing is going to have then two sets of forces. It's going to have the surface-surface interaction force from these two surfaces pushing, but it's also going to be load being carried in the cement, which I'm going to load and moment, and I'm going to designate those with bars. Okay. This model now, okay, wait, we're kind of keep it as simple as possible, but we had it gets more complicated now because it has to have a radius, the parallel bond. How wide is this thing? Okay. It also is going to have the stiffnesses of the cement, because the cement itself now is a deformable thing. So it's going to have a normal and shear stiffness. These are going to be stiffnesses per unit area because they're operating over a cross-sectional area that has a length of 2R bar. And then there has to be a concept of strength. And we'll talk about what that's going to be. But essentially, it's going to have the same idea. This is going to break in a normal mode, in a tensile mode, which is a normal mode, or it's going to break in a shear mode. And again, it's representing these glass beads cemented with epoxy. This is a good physical manifestation of the physics of a parallel bond. By the way, this is Rune Holt, is a rock physics professor at Trondheim, in Trondheim, Norway. He does all this work mainly for oil companies, where he looks at sandstone formations and he looks at things like, when was the cementation placed? Did the sandstone get compressed and then cemented, or did it get cemented and then compressed? All these things have big effects on the behavior of the cores. And so he developed this ability to build synthetic sandstone and test all these different things. And so this is one of the things he did here. He has this material, and then he wrote a journal paper where he compared the behavior of this material to a parallel bonded material. So that's an interesting thing. There really is a correlation. Now that's all we're going to do to talk about parallel bonds. We're going to look back now and look again. Now we're going to talk about so granular, linear contact model, bonded. You get different behavior when it's bonded. It can take tension. Let's put that aside for the moment and let's return to granular material. And so we're going to do flow from a hopper unbonded. So called dohopper.dvr. This one's going to look familiar. Where is this thing? Okay, talks. Here's my old-fashioned PFC. Call dohopper.dvr. There it is. And this is again that one cycle. Nothing happens. It's just sitting in static equilibrium. Delete wall 3, which is the bottom wall. Now cycle. And you can watch this thing go. We should make this should be like a screensaver that someone has, and you could have this thing make a bigger system and you could watch this thing evolve. There we go. Force chains. It's trying to form a stable arch. It's not able to in this case. Notice the shear load. Notice how these force chains are not perpendicular to the wall. There's a shear component. That's what's happening because there's friction here in this system. Friction on the discs and friction at the interface between the balls and the walls. Okay. Let's do this now. Restore hopper2.save. File, restore. And let's plot, show. There we go. Now I want to illustrate a certain thing here. Oh, let's give it friction now. Really high friction. So property friction 2.6. Friction coefficient of 2.6. That's unrealistic, but it still makes, you can still do it. So let's make high friction. Okay. Friction is what gives a granular material strength. It's the only thing that can give it strength is friction. But now we're going to delete wall 3. If I can type delete wall 3. And now I'm going to cycle. And so now it goes, but there's such a high friction. Oh, look, these guys are still falling, but it's locked up. Okay. The only thing I changed was the friction coefficient of the system. Add ball red. Now let's zoom in on one of those balls. Plot, add, ball, red, range, ID 103. Let's see, did I get that right there? Oh boy, let's zoom in now. Okay, there's one guy, and notice this big arch that's formed of high compression. This is the stabilizing arch, right? If you build a stone arch bridge, right, same type of thing. Here's the compression getting carried from here into the two side walls, right? Notice the high shear forces to withstand that. So this is in equilibrium. Now let's look at this guy, an important guy. What if we blow that guy away, right? We're going to disturb this. This also happens in ore passes in mines. Sometimes the stuff gets jammed up and then they have to go and they put explosives in and they try to blow it up at the bottom and hope that they're going to shake it all loose. So I'm going to say delete ball, range, range, range ID 103. Watch, look at that red ball. Boom. We deleted it. We're out of equilibrium. Now we're going to cycle. Oh, is it going to lock up? Oh, it locked up again. Okay. But again, you get the idea, right? We can change anything at any time in these systems. All right. So that gives us that concept. Here you've seen my little quote from Victor Hugo about falling grains of sand. We're going to do the same thing. Hopper 3 dot dat. Going to see, you saw this before. Whoops. Sorry. Hopper, what was I supposed to do? Hopper 3 dot dat. Okay. Now I've bonded this thing. It's already have a couple breaks at the top just from the process of creating it. Now I'm going to delete wall 3 and cycle a lot. And now again, you get the idea. Now you've got damage happening and it's breaking as it goes. And we're going to, I don't know if you ran this farther, I don't know if it's ever going to stabilize or not. Okay, but you get the idea. Breakages in tension. Some of the breakages are in shear. Tension is red, shear is blue. We draw these things. These are how we represent micro cracks. We basically say, right, see these two guys, there used to be a bond there. If it's an intact bond, there's a black line. So that line broke, and then we draw this guy to represent the crack. See, look at this. This guy broke as well. This guy broke as well, right? You get the idea. Whoop. All right. Shut that down. There's the idea. We talked about this, Lucretius. You really should get this book. It's a super interesting read. Okay, now this is a fun one. Okay, this is going to test your physical intuition. Okay, what do we have here? We have an annulus. This is a 2D model. This is like the air hockey table. We have a whole bunch of air hockey discs that are confined between two sets of walls. There's an inner set of walls and there's an outer set of walls. And so what we're going to do is we're going to pack them in there to begin with. And then once they're packed and they're static equilibrium, we're going to take this thing and we're going to, the entire system about the center, the walls are going to rotate. They're going to rotate in a counterclockwise fashion. Okay. We're going to first run this with all the particle contacts have zero friction, and the ball and the contacts at the interface with the walls have zero friction. So the whole thing is frictionless. So the question for you is, when there's no friction on here and we spin the walls, what the heck are the particles going to do? What's my thing? Wall filt fric 0. File call. We're also going to learn a little bit about packing. So we created the walls to begin with, and we have a command in PFC to generate a cloud of particles. And we can generate them so they don't overlap initially. So there we go. There's all the particles. They're not overlapping. If we cycle this now, nothing's going to happen because there's the contacts. There's nobody in contact. There's no forces here. They're just going to sit there. So what we're going to do now is we're going to proportionally scale the radiuses of all the particles so that they overlap. Watch. Make them all bigger. Boom. See all the overlaps? Because there's an overlap now, there's going to be a normal force acting because it's got a normal stiffness, right? So now we have to cycle this thing and let it all pack and come to equilibrium, come to static equilibrium. So there we go. Those are the current force chains. We're drawing black, green is now compression. Those are the force chains, big, high, crazy force chains because of high, crazy overlaps. Now everybody's frictionless, readjust. You can see the system readjusting itself. And there's like, you can see those rearrangements that are occurring still a little bit. And we're going to take 1,000 steps and we're going to say we're close enough. We're not 100% in static equilibrium, but we're close enough. So it's packed tighter here than it is over here, right? Higher values, thicker lines, right? Look at these guys. They're kind of shielded by the big high compression chain that's over here. Now, spin this baby. See what happens. Well, first get rid of the force chains. Now spin it. Oh. Wait, I did the wrong one. Frick 0. Oh, this is no fun. I'm sorry. I'm too excited. I ran the wrong one. Hold on. 0 friction. You can watch it pack again. This is always the first step of PFC modeling typically. You got to get a packed system. Especially if you're going to bond it, you got to get a packed system. Okay, here we go. Let them get packed. Like this would have taken like 5 seconds in PFC modern. Here we go. There, wow, look at that. Look at it flowing. Watch this area. Watch the red guys as they get perturbed as this thing flows around the corner. Frictionless. But they're still interested because they got these weird corners here, right? If I go a little further now and I show you the force chains, here's the force chains. It's basically sliding along those surfaces, but then it's getting mixed in the corner here. That's where all the complication is coming into play. And so that's my system, right? So that system mixed it up, okay? Now, what's going to happen if I have a non-zero friction coefficient? It's going to stay coherent because friction is giving this system its strength. So let's do that. Continue. Boom. Now there's this still even more interesting. It's kind of locked in place. Do you see it vibrating? Because it's not super tightly packed. And so those masses and springs are wiggling around back and forth. Look at the force chains. You can see here, I don't know if you can see it well enough. See how those force chains are changing as it's wiggling around? It's mainly locked, big high compression here, big high compression there, but it is like vibrating. I think we can zoom in to look at that vibration better, right? Let's continue to cycle. Here you go. See how it's vibrating? See those forces changing a little? Da, 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 da. Now this is because we have no damping. If we had damping, we would take that thing out. Now this is dangerous because I don't remember the damping command from 2008. Prop damp 0.7. Is that the command? Oh, it did it. It's still, forget what I said. I don't remember why. It might not be how I do the damping in this old PFC. All right. It shows that you shouldn't go off of script. So there we go. Friction gives strength. All right.